a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. In this episode, we examine the simulation theory, the idea that our reality could be an artificial environment generated by an advanced intelligence. We will look at why serious thinkers even consider it, what kinds of evidence people point to, and what that evidence does and does not show. We will move from simple, everyday observations to bigger questions in physics and computing, always separating what is solid from what is speculation. We will also talk about the strongest objections, because a case is only strong when it can survive criticism. The goal is not to scare you or convince you at all costs, but to explain the argument in plain language, so you can feel the shape of it for yourself. Tonight, we go through the case for the simulation theory. Imagine you are playing a video game with a huge open world. You can walk for miles, climb mountains, and look out over oceans. If the game is well made, it feels real enough to forget for a while that it is code. But under the surface, the game engine is doing something very specific. It does not compute every leaf on every tree all the time. It only loads what you can see. It uses shortcuts, approximations, and rules that are good enough for the experience. Now take that idea and stretch it until it becomes a question about everything. What if our universe is like that? What if the world is not the base layer of reality, but a generated layer? A kind of environment, a place where minds can exist and interact. The simulation theory is not one single claim, it is a family of claims. Some versions say we are in a computer program built by future humans. Others say we are in a simulation built by an alien civilization. Some say it is a training world. Some say it is art. Some say it is a side effect, like a laboratory model that accidentally became detailed enough for conscious observers to arise. Most people hear the idea and think of movies or jokes about glitches. But in the last few decades, the idea has also appeared in serious discussions. Philosophers have asked whether we can know the true nature of reality from inside it. Physicists have noticed how often nature seems to use simple rules and mathematical structure. Computer scientists have built worlds where simple code produces complex behavior. And in the middle of it all is a basic tension. If technology keeps improving, it seems possible that someone could one day simulate worlds like ours. And if they can simulate one, they can simulate many. The strongest case for simulation does not come from one perfect piece of evidence, like a fingerprint on the window. It comes from a stack of smaller points that, together, make the idea feel less crazy than it first sounds. Tonight, we will lay out those points. We will also be honest about the gaps, because the simulation theory is powerful as an explanation, but it is slippery when you try to test it. To keep things clear, we will use a simple approach. First, we will talk about why anyone would think this is even possible. Then we will talk about the kinds of evidence people claim to see. After that, we will talk about what would count as real evidence and why it is so hard to get. And finally, we will talk about what it would mean for your life if it were true. Not in a dramatic way, in a quiet way. Let us start with the most basic piece: possibility. If you go back a few hundred years, the idea that you could store a library in your pocket would sound like magic. The idea that you could talk to someone across the planet in real time would sound like a miracle. But technology does not feel like magic when you live inside it. It feels like tools. Computers are tools for doing math fast, but they are also tools for making models. Weather models, traffic models, models of atoms, models of entire galaxies. And in games, they are models of worlds. We already build simulations. We simulate physics enough to make a convincing explosion on a screen. We simulate crowds. We simulate economies. We simulate the spread of diseases. Most of these simulations are rough and simplified, but the direction is clear. More power, better models, more detail. When people argue for simulation, they often begin with a thought experiment. Imagine a future civilization that survives long enough to master computing. Imagine they have computers far beyond ours. Imagine they can model a human brain, or even upload a mind. Imagine they can render an environment for that mind to experience. At that point, the question is not only whether they can run a single simulation. The question is, how many? A powerful computer could run many copies, or many variations, like scientists running experiments. If they run a vast number of simulated worlds, then the number of simulated observers could far outnumber the number of original base reality observers. This leads to a probability argument. If there are many more simulated minds than base reality minds, then any randomly selected mind is more likely to be simulated. That is the basic shape. It is often called a simulation argument. It does not prove we are simulated. It says that under certain assumptions, it would be surprising if we were not. But assumptions matter. You need to assume that conscious experience can be created by computation. You need to assume that advanced civilizations will want to do this. You need to assume they can do it. And you need to assume they will run many simulations. Still, even if you reject the probability part, you can feel the point. The idea is not obviously impossible. And once something is not impossible, it becomes a candidate explanation, even if it is extreme. Now let us shift from possibility to the more interesting question. What makes people think they see hints of it? One popular category is the idea of limits. In computing, there are limits everywhere. Bandwidth limits, processing limits, memory limits. If reality were computed, you might expect to see signs of resource limits. People look for anything that feels like a cap. The speed of light is one of the biggest caps we know. It is a universal speed limit. No matter how hard you push, information does not move faster than that in normal space. To some people, that feels like a rule in an engine, like a maximum update speed. But there is also a perfectly good physics explanation. The speed of light is not a speed limit like a road limit. It is built into how space and time relate. It is part of the structure of the universe as described by relativity. Still, the simulation-minded person says, a simulation would also need consistent rules. A speed limit is the kind of rule you might include if you want a stable world. Another limit is the quantization of nature. When you look closely, energy comes in chunks. Light comes in photons. Particles have discrete properties. You can spin a particle and you do not get any spin you want. You get specific values. Again, physics explains this through quantum theory. But someone might say, discrete values look like digital representation, like bits, like pixels. That leads to the most famous metaphor, the universe as a pixel grid. In a digital image, you can zoom in and see pixels. In a simulation, you might expect a smallest unit of space, like a pixel of reality. Do we see that? not directly. Space, as far as we can tell, looks smooth at the scales we can measure. But there is a concept called the Planck length, a scale where our current theories stop working well. It is so small that it is beyond direct testing with current technology. Some approaches to quantum gravity suggest space may be discrete at the smallest scale. Others do not. So the evidence is not clean. But the idea remains. If there is a smallest unit, it would feel a lot like a digital grid. Another category is mathematics itself. Why is the universe so well described by math? Why do equations match reality? Why do we live in a world where simple patterns can explain so much? This question is old. It existed long before modern computers. Some people say math works because we built it to describe patterns, and the world is full of patterns. Some say math is the language of reality itself. For simulation thinkers, the mathematical nature of physics feels like a clue. Code is math. Computation is math. If the world is computed, of course it would be mathematical. The deeper you go, the more you would find structure. But there is a danger here. We might be confusing our map with the territory. Just because math describes something does not mean it is literally made of math. Still, the simulation case likes this point because it fits. Now let us look at a more concrete claim that often comes up, the idea that physics seems optimized. In many games, developers tune their engines. They choose rules that create stable gameplay. In our universe, some physical constants appear to be set in a narrow range that allows complex structures like atoms, stars, and life. If some constants were slightly different, the universe might be lifeless. This is often called fine-tuning. There are many debates about it. Some think it is an illusion. Some think it is real. Simulation theory is one possible explanation. A creator could set the constants deliberately. Another explanation is the multiverse. Many universes exist with different constants, and we are in one that allows observers. Another explanation is that we do not yet understand why the constants have the values they do, and future physics will show they could not be otherwise. Fine-tuning is not evidence for simulation in a strict sense, but it is one of the strongest emotional supports. It makes people feel that the universe is designed in some way. And if you already think in terms of design, simulation becomes a modern version of a designer. Now we should talk about information. In the last century, physics has been reframed in terms of information more and more. There are deep links between entropy and information. Black holes seem to store information on their surfaces. There are hints that space itself could be related to information. Some physicists talk about the universe as an information processing system, not as a metaphor, but as a serious viewpoint. If that is correct, then simulation feels closer, because computers are information processors. But again, we must be careful. Saying the universe processes information is not the same as saying it is running on a computer that sits somewhere else. Let us slow down and separate the strongest points from the weaker ones. The weakest evidence is random stories about glitches. People talk about seeing repeating patterns in life, like the same person appearing twice, or the same event happening twice. They talk about odd coincidences or strange feelings. These are not reliable. The brain is a pattern finder. It is built to notice repetition. It is also built to tell stories. Most glitch stories can be explained by memory errors, attention limits, and the messy way we perceive. so we will not rely on that. The stronger evidence is not a glitch you saw. It is the structure of physics and computation. The argument says that a simulated world could look a lot like ours, and the things we see do not rule it out. Still, that is not the same as evidence that it is true. A hypothesis that cannot be ruled out is not automatically likely. So what would count as stronger evidence? One idea is to look for artifacts. In an old digital photo, you might see compression blocks. In a simulation, you might see patterns that suggest a lattice, a grid. Some researchers have suggested that if the universe were on a grid, very high energy particles might behave in a slightly biased way, depending on direction, like how movement on a pixel grid can produce tiny directional effects. Cosmic rays, which are high energy particles from space, could potentially reveal such effects. There have been papers discussing how one might test this, but so far there is no clear, accepted detection. Another idea is to look for limits in randomness. Computers often use pseudo-random number generators. They produce sequences that look random, but are generated by rules. If the universe uses something like that, maybe there would be detectable patterns. But quantum randomness is strange. It looks truly random. Many physicists think it is not just ignorance, but real unpredictability. Others believe hidden variables could exist, deeper rules we do not see. A simulation could generate true randomness if it had access to a deeper random source, or it could fake it well enough to be impossible to detect from inside. So randomness is a hard path. Another idea is to look at the so-called observer effect in quantum mechanics. In simplified language, some quantum experiments show that until you measure a system, it does not have a single definite outcome. It exists as a set of possibilities. This is often misrepresented. Measurement does not require a human mind staring at an atom. Measurement means interaction with the environment. A detector, a particle, a photon. Still, the idea that the world becomes definite when measured is very tempting for simulation thinkers. In games, the world is rendered when you look, not because you are conscious, but because it is efficient. If reality behaves in a way that resembles delayed rendering, maybe it is because it is rendered. But quantum theory does not say the world is literally not there until you look. It says the properties are not in a definite state until interaction. And there are multiple interpretations. Some interpretations, like many worlds, avoid the need for collapse. They say all outcomes happen, and we are in one branch. Simulation theory can be combined with different interpretations. A simulation could implement collapse, or it could implement branching. It could implement hidden variables. The theory is flexible. Flexibility is not always good. A hypothesis that can explain anything can become unfalsifiable. So we need to ask, can simulation theory be tested at all? Some say it cannot. They say a sufficiently advanced simulator could hide any trace. They could adjust rules, patch artifacts, and prevent us from escaping. Others say we might still detect constraints. If the simulator is not perfect, there could be leaks, like a screen door, like a repeating texture, like a boundary. But would a simulator allow such leaks? Maybe. Maybe they do not care. Maybe it is a simulation left running, like a forgotten experiment. Now we reach a key point. The strongest case for simulation is not that we have direct evidence, but that we do not have a clear reason why simulation is impossible. and we can see paths by which it could happen. This is a different kind of argument than most science. It is a philosophical argument about likelihood in a large space of possible realities. Let us build the case carefully, step by step, in plain language. Step 1. It seems possible that consciousness could arise from physical processes. Your brain is physical. Neurons, electrical signals, chemistry. From that, you get experience. If consciousness arises from physical processes, then in principle, it might arise from a system that imitates those processes closely enough. That could be a brain in a jar, a brain replacement, or a computer model. Not everyone agrees. Some think consciousness requires something more than computation. But many thinkers and many working scientists assume that the brain is the basis and that it is possible to reproduce its function. Step 2. Computing power has grown fast. Not perfectly exponential forever, but in a steady march of improvement. Even if it slows, it might still reach levels beyond our current imagination. Step 3. If computing power reaches that level, it might be possible to simulate worlds in great detail. Not necessarily the whole universe, but a region, or a world that looks consistent to its inhabitants. Step 4. If you can simulate minds and worlds, you might do it for many reasons. Research, entertainment, history, training, or curiosity. Step 5. If you do it, you might do it many times. Now comes the probability step. If there are many simulations, then simulated observers could be common. This is the skeleton of the argument. The evidence in this framework is not a single measurement. It is the trend of technology, combined with the lack of a clear barrier. People often ask, but would it take too much power to simulate a whole universe? Probably yes, if you mean simulating every atom in the observable universe at full detail at all times. But a simulation does not need to do that. It only needs to be detailed enough for the observers inside. If you are simulating minds, you only need to render what those minds can observe. This is like a game engine. It uses levels of detail. Faraway objects are simplified. Hidden objects are not computed. If you never go to a certain star system, maybe it is never fully generated. Does that mean the universe would be fake outside our view? Not exactly. It could be generated on demand, or it could be computed in a compressed way, like storing a seed that expands into detail when needed. We already do this in procedural generation. You can create a huge world from a small seed and a set of rules. The world is not stored as a giant file. It is generated. Nature itself uses something like procedural generation. Simple laws produce complex outcomes. This is why simulation arguments feel strong, because the world already behaves like it is governed by compact rules. Now let us talk about a piece of evidence that many people call the strongest in a practical sense. The idea that the universe has a maximum information density. There is a concept called the Bekenstein bound. It suggests there is a limit to the amount of information that can be contained in a region of space with a given amount of energy. There is also the idea that the information in a region might scale with its surface area, not its volume. This appears in black hole physics. It leads to what is sometimes called the holographic principle. To a simulation thinker, this is exciting. It suggests the universe might store information in a way that resembles data compression. But this is still within physics. It does not imply an external computer. It could simply be how reality is. Still, The simulation theory can borrow this and say, look, the universe seems to have information limits. That fits the idea that it is computed. Now we should ask, what about the weirdness of quantum mechanics? Does it support simulation? Quantum mechanics is strange because it breaks our everyday expectations. It speaks in probabilities. It allows entanglement where particles share a state even across distance. It allows events that have no classical cause we can point to. Some people say quantum weirdness is exactly what you would see if reality is not a fixed object but a calculated output. Entanglement, for example, looks like two objects are linked in a way that ignores space. In a computer simulation, distant objects can be linked instantly because the underlying code can access both states without traveling through the simulated space. But physics does not allow faster-than-light communication with entanglement. The correlations are real, but they do not carry messages in the simple way people imagine. Still, it feels like a hint that the world is deeper than it appears. So far, you might notice a pattern. Many of these points do not prove simulation. They just show that the world is compatible with it. To strengthen the case, we need to talk about what kind of simulator we are imagining. If the simulator is like a human computer, then it has limits. It uses resources. It might have corners. If the simulator is like a god, then it has no limits, and the idea becomes indistinguishable from certain forms of religion. Most modern simulation arguments imagine something in between. A very advanced intelligence, but still part of some bigger reality. This matters because it affects whether there would be detectable artifacts. If the simulation is a research simulation, the creators might not care if it is detected. They might even want it detected. If the simulation is entertainment, they might want immersion, so they would hide artifacts. If the simulation is a training environment, they might include tests. Each version changes what we should look for. Now let us examine a different kind of evidence. Not physical evidence, but social and historical evidence. The simulation idea appears again and again in human thought, in different forms. Plato's cave is a story about people seeing shadows and thinking they are reality. In some religious traditions, the world is described as an illusion or a veil. This does not prove simulation, but it shows that the intuition is natural. Humans sense that perception is not the same as reality. Our senses are limited. Our brains construct a model. In that sense, every human already lives in a simulation of sorts, a brain-generated simulation based on sensory input. This can blur the debate. Some people use simulation to mean the brain's model. Others use it to mean an external generated world. Tonight, we mean the external one, the big one. So we should be careful not to confuse the two. Now let us consider the strongest evidence-like point, the rapid progress of virtual worlds. We are building worlds that feel more real each year. Graphics improve, physics improves, AI improves. Soon, virtual characters may act like real people. They may have conversations, goals, memories. At some point, it becomes hard to draw a clean line between a simulated character and a mind. This is not proof, but it is a hint about direction. It suggests that creating convincing worlds is not a dead end. It is a path. If you accept that path, then you accept that some future beings might create worlds like ours. Now ask yourself, if they can, why would they not? This is where the argument gets psychological. Humans like to create. We build toys, art, games, and models. If future beings share any of that curiosity, they might create simulations. And if they create simulations, they might create many. Now, here is a sobering thought. Even if you reject the probability argument, the mere possibility can affect how you see the world, because it invites you to question what is fundamental. But let us not float away. Let us anchor again. The best criticism of simulation theory is simple. It may not be testable. It may not predict anything new. It may be a story that fits everything. Science advances when a theory makes risky predictions, predictions that could be wrong. Can simulation theory do that? Some versions can, in principle. If the simulation runs on a grid, we might detect lattice artifacts. If the simulation uses compression, we might detect limits in complexity. If the simulation is updated in discrete ticks, we might detect time granularity. But each of these is uncertain, and each could be avoided by a simulator. So, the simulation theory may be more like a philosophical stance than a scientific theory. Is that bad? Not necessarily. Philosophy can still be true, but it means we should not pretend it has the same status as a well-tested physics model. Now let us explore what people mean when they say evidence for simulation in layman terms. Often they mean one of three things. First, they mean that the world behaves like information. Second, they mean that the world has limits like a system. Third, they mean that the future could create simulated worlds, so it is likely that such worlds exist. Let us take each and make it concrete. Information. In physics, information is not just data on a hard drive. It is a way to talk about the number of possible states of a system. The more information, the more detail. When you heat a gas, it spreads out, and its entropy increases. Entropy is linked to the number of possible microstates. That is information. In black holes, there is a famous problem about whether information is destroyed. Many physicists believe it is not. This has led to deep ideas about how information is stored. When you hear a physicist say, reality might be built from information, you can see why simulation feels near. Because information is what computers handle. Limits, the speed of light, quantization, maximum information density. These all feel like system limits. Future simulation. This is the probability argument. Now, to make the case stronger, we should confront the most common objections. Objection 1. Consciousness cannot be simulated. If consciousness requires something beyond computation, then simulation theory weakens. Because even if a world is simulated, the minds might not be. But we do not have evidence that consciousness requires magic. We have evidence that it is linked to brain states. Damage the brain, and experience changes. Change the chemistry, and experience changes. This strongly suggests that experience depends on physical patterns. Does that prove it is computable? Not fully, but it makes it plausible. Objection 2. Simulating a universe is impossible. As we said, you may not need to simulate everything at full detail. You might only need to simulate what is observed. Objection 3. The argument assumes advanced civilizations exist. This is important. If civilizations always self-destruct before reaching that level, then simulation becomes less likely. Some versions of the simulation argument include this as an option. Maybe very few reach the point where they can run simulations, or maybe they choose not to. Objection 4. Even if simulations exist, why think we are in one? This returns to the probability claim. If there are many, then the odds favor it. But if there are few, then maybe we are base. So the conclusion depends on unknowns. Objection 5. It is just a modern myth. This is also possible. Humans create stories that fit their era. Ancient people saw gods in the sky. We see computers behind the curtain. This objection does not disprove simulation. It warns us about bias. Now, what about the famous argument that if we were in a simulation, the creators would have shut it off once we started to suspect? This is a fun idea, but it assumes the creators care. Maybe they do not. Maybe they are studying what happens when inhabitants start to suspect. Maybe they cannot easily shut it off. Maybe we are in a simulation that is automatically generated and not closely monitored. Now we reach a calm but important part. What would it mean for you if it were true? If we are in a simulation, the laws of physics are still real to us. Gravity still pulls. Pain still hurts. Love still matters. Time still moves. The simulation would not make your life fake. It would change what you think is fundamental. Instead of atoms being the base layer, code would be, or something like code. But from inside, your experiences are still experiences. There is also a strange comfort in it. If reality is generated, perhaps death is not the end. Perhaps minds can be backed up. Perhaps the environment has a purpose. But we should not jump. Simulation theory does not automatically mean there is an afterlife. It does not automatically mean there is a plan. It only suggests a different kind of underlying mechanism. Now, let us build a clearer, layman-friendly version of the strongest evidence points as a list, but woven into story. Point 1. We already create simulations, and they are improving fast. Point 2. The universe is described by compact mathematical laws like code. Point 3. Nature has discrete chunks and limits that resemble digital systems. Point 4. Physics is increasingly described in terms of information. Point 5. If advanced civilizations can create simulated worlds, they may create many. Together, these points make simulation feel plausible. But plausibility is not proof. Now you may be wondering if it is so hard to test. Why do people talk about it? Because it is a powerful lens. It helps people think about reality in a new way. It also fits with current culture, and sometimes a lens can lead to real progress. When you think of the universe as information, you may ask new questions. You may find new connections. Some physicists have explored ideas like it from bit, the notion that physical reality arises from information. Others have studied how space-time could emerge from quantum entanglement. These are not simulation proofs, but they are related. Now let us slow the pace and take a long walk through some of the most cited pieces of the case. First, the ancestor simulation idea. Imagine humans survive for thousands or millions of years. They have vast computing power. They can simulate the lives of their ancestors in detail. They might do it to understand history, or to explore alternative outcomes, or to connect emotionally. If they can simulate one history, they can simulate many. They might run countless versions, each with small variations. If so, the number of simulated humans could be enormous. In that scenario, the chance that you are in base reality could be small. This is a clean argument. It does not need quantum weirdness. It needs only the assumption that such simulations are possible and common. Second, the rendering on demand idea. In quantum experiments, the behavior of particles depends on measurement setup. In the double-slit experiment, If you measure which path a particle takes, you get one pattern. If you do not, you get another. To many people, this feels like the world decides what to be when asked. A simulation could work that way. It could store probabilities and only produce outcomes when required. But physics itself might work that way without any simulator. Third, the cosmic code idea. The laws of physics can be written in short equations. That is astonishing. You can write a few lines, and they describe galaxies and atoms. In human-made systems, compact rules often indicate a designed engine. But again, the universe could simply be elegant. Fourth, the fine-tuning idea. The constants seem set for complexity. A simulator could tune them, but a multiverse could also explain it. Fifth, the limits idea. If there is a maximum speed, a minimum length, and a maximum information density, then the universe has boundaries. Those boundaries could be features of a computed environment, or they could be features of base reality. Notice how often we return to the same fork. This is why simulation theory is hard to settle. Now, some people ask a different question. If we are in a simulation, is there a way to communicate with the outside? Most likely, no. Not in any direct way. Any communication would be filtered through the rules of the simulation. But there is a thought experiment. If you were a character in a game, could you send a message to the developer? If the developer is listening, maybe. If there is a debug console, maybe. In some science fiction, people try to cause events that would show the simulator they are aware. In real life, there is no evidence of such a channel. Still, the idea reveals something. It shows how quickly simulation talk becomes spiritual talk. The simulator becomes a creator. This can be comforting for some and unsettling for others. Tonight, our goal is calm understanding, not worship, not panic. Now, let us ask the most grounded question. If you want to be rational about this, how should you hold the belief? A rational approach is to treat simulation as a possibility with uncertain probability. You can say it is not obviously false. There are arguments for it. There are arguments against it. We do not have decisive evidence. If you keep it in that box, it can be an interesting thought, not an obsession. Now, let us explore an often overlooked point that makes the simulation case feel stronger. The idea of compression and emergence. In many systems, the surface behavior emerges from deeper rules. You do not need to store every detail. You can store rules and seeds. Our universe seems to be like that. The same laws apply everywhere, at least as far as we can tell. This uniformity is exactly what you would do if you wanted a simulation to be consistent, but it is also what you might expect from base reality. Still, it supports plausibility. Another point is that physics seems to have a limited set of particles and forces. It is not an endless zoo. It is a structured set. This could suggest an engineered system, or it could suggest that nature is constrained by deep principles. Now, let us talk briefly about the idea that the universe might be a computation, even without an external simulator. Some philosophers and scientists have suggested that the universe is itself a computer. That computation is what it does. In that view, there is no outside computer. The universe computes itself. This is different from simulation theory, but it overlaps in language. If the universe is a computation, then the simulation metaphor becomes less dramatic. It is just a way to describe reality. But most people who say we live in a simulation mean an external one. Now, to keep the layman framing strong, let us use an analogy. Imagine you are reading a book. The characters live in their world. Their world has rules. The author decides what happens. From inside the book, the characters cannot see the author. They can only see the story. If a character started to suspect they are in a book, what evidence could they find? They might notice that the world is described in simple words, that things not mentioned do not exist until mentioned. They might notice that events happen in a way that makes narrative sense, but those are not perfect clues. A real world could also have patterns. Still, it gives you the feel. Now, perhaps the most honest conclusion we can reach is this. The strongest evidence for the simulation theory is not that we have detected a simulator. It is that the idea fits with several deep features of reality, and it fits with the trajectory of technology. It is a hypothesis that becomes more plausible as our own simulated worlds improve. That is the core. Now, if you are listening and you want to feel the argument without the noise, hold this single sentence. If minds can be simulated and simulated worlds can be created and advanced civilizations are common, then simulations may be common and we might be in one. That is the case. Now, before we close, we can take a longer, slower path through the strongest pieces of the case, the parts that people return to again and again. Think about how you know the world at all. You do not touch reality directly. You have senses, eyes that take in light, ears that take in pressure waves, skin that feels contact and temperature, and then your brain builds a model. It combines the signals, compares them to memory, and creates a picture of a room, a street, a sky. This model feels like reality, but it is not the same thing. It is an internal world, a private world. It is so convincing that you rarely notice how much work is happening behind the scenes. If you have ever dreamed, you know how deep this can go. In a dream, your mind can create a whole place, with rules and emotions and meaning, and it can feel real until you wake. This does not prove the outside world is simulated, but it shows something important. Your lived experience is already generated, in part, by a system that interprets and renders. Simulation theory takes that familiar idea and aims it outward. It says, what if the outer world is also rendered, also generated by deeper rules? Now let us return to the probability argument, because this is often called the strongest logical support. It can be explained in everyday terms. If you walk into a forest and see a single tree, you might think, this tree is rare. But if you walk farther and see thousands of trees, you stop thinking the tree is rare. You start thinking trees are normal. The simulation argument says something similar. If a civilization can run many simulated worlds with conscious beings, then simulated beings could be very common. If they are common, then it is not strange to think we might be one of them. But notice how this depends on the word can. Can they do it? Can they simulate minds? Can they simulate a world with enough detail? Can they afford the resources? To understand this, picture a simple scale. On one end, there is base reality, the original level. On the other end, there are countless simulated worlds. If simulated worlds are rare, then we are probably base. If simulated worlds are common, then we are probably simulated. The problem is that we do not know which side we are on. Still, there is a reason this argument feels weighty. It turns simulation from a wild story into a question of numbers. Now let us talk about what those numbers would require. Would you need to simulate every atom in the universe? Not necessarily. A mind does not need to measure every atom. A mind has limited senses. Even the best telescope has limits. Even the best collider has limits. You can only observe so much. A simulation could take advantage of this. It could run a local world at high detail. It could run distant parts at lower detail until they are observed. It could use rules that generate consistent results when tested. In other words, it could be like a world with lazy loading. You may not love that phrase, but the idea is simple. A system can save resources by only computing what matters to the observers inside. Does our universe look like it uses lazy loading? Some people point to quantum mechanics here. They say the world is described by probabilities until measured. That resembles a system that does not pick a single outcome until it must. But quantum mechanics might be telling us something deeper, not something artificial. So the honest statement is this: quantum mechanics is compatible with simulation. It does not prove it. Now let us explore a different kind of evidence claim that often sounds more technical than it needs to. People will say the universe is digital. What do they mean? Usually they mean that the universe has discrete units and rules. Photons come in quanta. Energy comes in packets. Matter has a small set of particle types. Atoms come in countable pieces. If you grew up in a world of screens, this feels like pixels. But physics can be discrete without being a computer simulation. A better way to put it is that the universe appears to have a limited menu of building blocks. And that limited menu is a reason some people feel the world could be generated by a compact set of rules. Now let us talk about another argument that is often misunderstood: the idea of fine-tuning. In simple terms, some constants in physics seem to have values that allow complex structures. If you change them slightly, you might not get stable atoms, or long-lived stars, or chemistry. If this is true, it invites three main explanations. 1. The constants are set by a deeper law, and they could not be otherwise. 2. There are many universes with different values, and we are in a rare one that allows observers. 3. Someone set the values, like parameters in a program. Simulation theory fits naturally into the third. But it is not the only option. So the best use of fine-tuning in the simulation case is not as proof, but as support for the idea that our universe could be selected or designed. Now let us turn to something that feels very modern: the idea that the universe runs on information. There is a reason this idea keeps growing. When physicists study black holes, they find that black holes behave like objects with temperature and entropy. Entropy is a measure of how many microscopic states are consistent with what you see. When you learn that a black hole has entropy, you learn that it stores information. This has led to the idea that the surface of a black hole contains the information about what is inside. That is strange. It suggests that the universe may store information in ways that are not obvious from everyday life. To a simulation thinker, this is a big hint, because information storage is what computers do. But again, a universe that stores information is not automatically simulated. It could simply be what reality is. Now, there is another line of thought that is simple but powerful. If we are in a simulation, then the outside world must be more complex than the inside, because it must contain the computer running the simulation, unless the simulation is self-running, like a mathematical object. But if we imagine a computer somewhere, then there is an outside. and that outside would have its own physics, that physics could be very different, and that outside could itself be simulated. This leads to an idea called simulation nesting. A simulated world could contain beings who run simulations. Those simulations could contain beings who run simulations. It could go down many levels. If that happens, then most observers might be many levels deep. This again pushes on the probability argument, but it also adds a strange twist. If we are nested, then the simulator might not be a godlike being. It might be an ordinary being in a higher layer. It might be running us for reasons that feel small. Research, a school project, a game. That thought can feel unsettling, but it can also be grounding. It suggests that even if there is a creator, they may not be morally perfect or all-knowing. They might be like us. Now let us talk about what people call glitches, but in a more careful way. A glitch, in the serious sense, would be a repeatable, testable anomaly, not a memory error, not a strange coincidence, a real anomaly. Something like a hard cap on resolution, or a repeating pattern that shows up in measurements. Do we have that? Not so far. Modern physics is full of surprising results, but they are consistent with the theories that predict them. They are not like a broken texture in a game. So the best statement is that we do not have direct glitch evidence. Now let us look at another point people bring up. Why does the universe seem to be computable at all? When you write down equations, you are making a model. The surprising part is how well the model matches. This is sometimes called the unreasonable effectiveness of mathematics. For simulation thinkers, it is not unreasonable at all. They say, of course, math works, because reality is built from rules. But here is the counterpoint. Math may work because we select the parts of math that match the world. We build math as a tool, and we use it where it fits. So math being useful does not prove the world is code. Still, it is another piece that supports plausibility. Now let us discuss the strongest layman-friendly evidence claim that you can feel without a physics background. It is the direction of virtual reality. If you look at the last 50 years, screens went from simple shapes to photo-like images. Games went from flat worlds to complex, immersive spaces. Computers went from basic calculators to systems that can generate voices, images, and whole scenes. This direction suggests that one day, a simulated world could be convincing enough that a person inside could not tell. If that day comes, then simulations are not science fiction. They are engineering. And if they become cheap enough, then there could be many. This is the part that many people find the most convincing, because it is not abstract. It is a trend you can see. Now we should ask, does the simulation theory change how you should live? Most likely, it changes very little. If you are kind in base reality, you should be kind in a simulation. If you care about truth in base reality, you should care about truth in a simulation. If you protect your health in base reality, you should protect your health in a simulation. Because your experience still matters. There is an old idea in philosophy called the problem of other minds. You cannot prove that other people are conscious. You assume it because it fits the evidence and because it is the moral thing to do. Simulation theory is similar. You cannot prove the outside layer, but you can hold the possibility with humility. Now let us address a fear that sometimes appears. If we are simulated, does that mean someone is watching? Not necessarily. A simulation could run without attention. A A simulation could be recorded and reviewed later. A simulation could be automated. You do not need a watcher at every moment. So if the idea brings anxiety, it helps to remember that the simulation argument does not require surveillance. It only requires a process. Now, there is also a hopeful thought. If we are simulated, then perhaps the outside layer has more room, more time, more options. Perhaps death is not final. Perhaps minds could be copied. But again, this is not guaranteed. A simulation could be cruel. It could end. It could be deleted. The theory does not promise safety. So the most balanced stance is calm curiosity. Now, another part of the case involves the idea that physics uses error correction. In computers, we use error correction to protect data from noise. Some researchers have noticed that certain mathematical structures in physics resemble error-correcting codes. This is technical, and it is easy to exaggerate. But the gentle, layman takeaway is this. Sometimes the math of physics resembles the math of information technology. That resemblance does not prove simulation, but it adds to the feeling that the universe and computation are deeply linked. Now let us revisit the question of testing, because it matters. If a theory cannot be tested, it is hard to know what to do with it. A healthy approach is to treat simulation theory as a live hypothesis that might someday connect with measurable questions. For example, if future physics suggests space is discrete, we can ask if that discreteness has patterns. If future experiments find limits that look like a grid, we can explore. If future computing and brain science show that minds can be uploaded, the probability argument becomes stronger. So simulation theory sits at a border. It touches philosophy, physics, and technology. Now, as we approach the end of our long walk, we can return to a quiet summary. The case for the simulation theory is strongest when it is modest. It does not claim we have proven anything. It claims that, given what we know about computation, given the rule-like structure of physics, and given the possibility of many simulated worlds, it is reasonable to consider that our world could be generated. The evidence is not a single smoking gun. It is a pattern of compatibility, and the objections are real. We do not know if minds can be simulated. We do not know if advanced civilizations survive. We do not know if the hypothesis can be tested from inside. So the best posture is open, calm, and careful. We can also add one more quiet layer to the discussion, a layer that many people skip. Ask yourself why the simulation idea feels powerful right now. It is not only because of physics. It is because our lives are becoming more mediated. We spend hours inside digital spaces. We talk through screens. We work through software. We make memories with cameras. We navigate with maps that are generated in real time. In a sense, modern life trains your mind to accept that an experience can be real to you, even if it is delivered through a system. That mental training makes the simulation hypothesis easier to hold. But it also introduces bias. If you live in a world of computers, you will naturally use computer metaphors for everything. So we should be honest about that. At the same time, the computer metaphor is not random. It matches real structure. The universe behaves in a rule-based way. We can write laws that predict outcomes. We can compress huge ranges of phenomena into a small set of equations. That is why the metaphor keeps returning. Now here is a simple thought experiment you can carry with you. Imagine you are inside a perfect simulation. and the simulator wants you to never discover it. What would the simulator do? It would make the rules consistent. It would make the world stable. It would make measurements match theory. It would allow curiosity, because curiosity is part of a believable world. And if the simulator were very good, it would make every attempt to find a boundary fail. Not by looking suspicious, but by looking like normal physics. If that is true, then we should not expect to find a dramatic trapdoor. We should expect that if the simulation is detectable, it will be detectable only through subtle constraints. That sets expectations. Now consider the opposite. Imagine the simulation is not perfect, not because the creators are careless, but because no system is infinite. Then constraints might show up as deep limits, a maximum speed, a minimum length, a limited set of particle types, a finite amount of information in a region. In that view, physics itself could be the fingerprint of limitation. This idea is not proof, but it is one reason people call these limits evidence. Now, let us talk about a related concept that is easy to understand: compression. If you want to store a long song, you can store a compressed file. When you play it, the file is expanded into sound. If the universe were computed, perhaps much of its detail is compressed in a similar way. Instead of storing every detail explicitly, the simulation stores rules and seeds. Then, when an observer measures something, the rule expands into a specific outcome. This is similar to procedural generation. A world can be huge without being fully stored. Now think about physical law. Physical law is like a compressed description of reality. You can write a small equation and it generates endless phenomena. That resemblance does not prove simulation, but it makes the hypothesis feel like it fits. Now, another gentle point. If we are in a simulation, then the simulator might not care about human meaning. But meaning can still exist. Meaning is something minds create. It is a pattern of value. A simulated world can still contain love, art, loyalty, courage, and tenderness. A simulated world can still contain suffering. So the moral weight of life does not vanish. This matters because some people fear that simulation makes everything pointless. It does not. If anything, it raises an old question in a new form. What gives a life value? Is it the material it is made of, or the experience it contains? Most of us, in quiet honesty, answer that it is the experience. Now, one more objection we should face, because it is strong. Even if simulations exist, why assume the simulators are like us? Maybe the outside layer does not run on anything like computers. Maybe what we call computation is a low-level shadow of a deeper process. If so, then our whole framing could be wrong. This is true. Our metaphors are limited, but simulation theory, in its best form, is not married to one kind of machine. It is a claim that the world we see could be an output of deeper processes that can generate observer experiences. In that sense, simulation is a placeholder word. It points at the idea that our reality might be a layer. Now, if you keep that in mind, the case becomes both simpler and more humble. It says, the world might not be fundamental. That is all. And that is a thought humans have carried for a very long time, in many forms. Now, one last calm pass through the core question, stated as simply as possible. If you could only keep one idea from tonight, it could be this. We do not know what the base layer of reality is. We know what our layer feels like. We know it follows rules. We know it can be described with mathematics. We know we can build small simulations inside it. And we know that, at least in principle, bigger simulations could be built if minds and environments can be modeled. From those points, the simulation theory becomes a reasonable possibility, not a certainty, a possibility. And if it is a possibility, then the smartest way to carry it is like a stone in your pocket. You can feel it is there, but you do not need to hold it in your hand all day. You can live your life. You can care for people. You can enjoy small things. You can do your work. And if you ever feel the question rising again, you can return to the simple map. Is it possible? Is it likely? Is it testable? What would change if it were true? Those 4 questions are enough to keep you grounded, and they keep the idea from becoming a superstition. Now, to close, we will step away from argument and return to quiet. Whether the universe is base reality or a generated layer, you are here. You are breathing. Your mind is moving through this moment. You do not need to solve the ultimate question tonight. You can let it rest on a shelf in your mind, like a book that can be opened later. If tomorrow you hear a new claim online, a new proof or a new glitch, you can meet it with steady calm. You can ask, is this repeatable? Is it measurable? Is there a simpler explanation? Does it actually point to a simulator? Or does it only point to how strange physics and perception already are? That kind of calm thinking is not cold. It is protective. It keeps you from being pulled around by fear or hype. And it also keeps the wonder intact, because wonder does not need panic. Wonder can be quiet, and you can allow the world, whatever it is, to hold you gently. If reality is base, then you are part of something ancient and deep. If reality is simulated, then you are still part of something ancient and deep, just with an extra layer behind it. Either way, your small moments are not made smaller. They are made more precious because they are happening at all. A breath, a warm blanket, a quiet room, a mind drifting towards sleep. These are real, no matter what the underlying mechanism is. Let that be enough for tonight, now. This was a quiet archive story, where the story ends, sleep begins.